Okay, so this is our last lecture, and this is very dependent on the things that we have learned last week, the consolidation. So today's topic is one-dimensional settlement. So let's first see what is settlement. The settlement is defined as the compression of the soil layers due to loading applied on or near its top surface. So when you consider the total settlement, it has three components: elastic settlement, which is happening instantly when we load the soil. So when we load the soil, there is an initial elastic immediate settlement. We call it elastic because if we take this load out, that the soil will come back to its original position. So that deformation we call the elastic settlement. Is the rearrangement of the grain due to changing stress, resulting in a reduction in void ratio and instant settlement. In most texts, immediate settlement is considered to be an elastic process. So elastic means it's going back to its original position. Primary settlement is what you have learned last week, which is the consolidation, is the gradual rearrangement of grains as water is expelled. So when we talk about the primary settlement or the consolidation, we discussed last week, we consider saturated soil. So we have the soil and the water, and when we apply a vertical load, this water can drain through the soil, depending on there are three things actually which determines the amount of settlement, or as an amount of consolidation, and how long it will take, how fast it is happening. Can you remember the three things, Sean? One is the hydraulic conductivity of the soil. The second is the thickness of the soil layer. And the third one is where it is, the position. So depending on these three, we know last week we discussed how to find the how fast it is happening and how much of settlements happening. So today also we are doing the same thing, because when you consider the one-dimensional settlement, one-dimensional, I'll explain why we call it one-dimensional later on. We mainly focus on the primary settlement, consolidation, which we discussed last week, because elastic settlement is very less, and also it is elastic, it is coming back to its original position. And the secondary settlement means the settlements happening over the years. So that means, for example, if we have organic matter in the soil, it consists of many chemicals. So these chemicals can react, and the clay mineralogy can change. When the clay mineralogy changes, it changes the volume as well. So that kind of settlements which is happening with the time, that we call the secondary settlement. So here in this module, we are mainly focused on this primary settlement, which is the consolidation. We already have discussed that, because when you consider the three components, you can see in this chart as well. So the major part is the primary settlement. So that's why we are focusing on this. The immediate settlement is less, and also the other part also very the secondary is very small as well, this much. So we are mainly we do all the calculations only considering this. We are ignoring this and this for the time being. Any question, Sean?
Not so far.
All right, now let's see why we call it one-dimensional settlement. So when we consider, so in this one we have soil layers 1, 2, and a rock, and we have the water table over here, and we have an embankment here. So since water can flow out of saturated soil in any direction, the process of consolidation is essentially three-dimensional. So water can flow any direction, so can be like settlement can happen in X, Y, and Z directions. However, in most field situations, water will not be able to flow out of the soil by following horizontal. So it's not going, in most of the cases, it's not going horizontally because of vast expanse of the soil in horizontal direction. Therefore, the direction of flow of water is primarily vertical. So because of that, we call the settlement is one-dimensional. We have a one-dimensional settlement as everything is flowing, water is flowing down. We're not considering water flowing X or the Y direction. As a result, the soil layer undergoes one-dimensional settlement or one-dimensional consolidation. It's in the vertical direction. So let's see how it is happening. So at the beginning, we have a volume of soil. We took we did it in week 1 as well. We consider it as VS. And if the void ratio at the beginning is E0, the void space is VS times the V0. So we can write the total volume at the beginning as VS plus this, adding these two together. Now, after we applied a force, when we consider there is a delta E change in the void ratio, we can say this doesn't change because the volume of soil doesn't change, but the volume of voids changing. Now we have E0 minus delta E. Delta E voids is not there because the water has drained out. So the void volume will be VS times this. So the total volume is now changing. Now, if you consider the strain means delta L over the L, or else delta V over the change in the volume divided by the initial volume. The strain in the Z direction is delta V divided by delta V divided by V0. So we discussed this last week, if you can remember. When you do fundamentals of mechanics, you know you plotted the stress and the strain in engineering materials. I think also you plotted the stress and the strain for metals. It came like this. So likewise here, stress means the force divided by the area. Strain means the change in the length divided by the initial length. Strain can be, you can consider the length or the area strain in 2 dimensions or strain in the 3 dimensions. So when you consider 3-dimensional strain, that will be the change in the volume divided by the V0. Now, any questions so far, Sean?
No, that makes sense.
So now let's see to change in volume. So you have, this is your initial volume and this is your final volume. Final volume minus the initial volume is your change in volume. You divide that by the initial volume. Now, if you substitute these values over here, you can say you have this minus this divided by the initial. So you get this. So you have a minus because when you minus V0, when you do this, you have a minus delta E. So that is minus delta E divided by delta E times V0 divided by V0 times 1 plus E0. That is the initial. So this V0 and V0 will cancel out. So you ending up with this. So this equation is needed. Even though when we consider the volume strain, we last slide we mentioned that the change in the volume is only happening in the Z direction. It's not happening in the X or the Y. So we can say this is equals to the Z direction strain. So that Z direction strain is equals to whatever we found here. So this is a minus delta E divided by 1 plus 1 plus E0. So this equation is important for us. We used this last week. If you can remember, I told you this equation. If you can't remember how we prove it, just take it as a known equation. Can you remember that?
Yeah, I remember going through at the beginning. I don't remember using it in any of the questions.
We used it in a question in the tutorial.
Oh yeah, the last one. Yep.
Yes. So again, you don't have to remember any of this. You only need to use this one, but this came like this. Okay. Now let's see the settlement. This is the strain. Now we need to relate the settlement as well. Settlement is the S. If you can remember, week 1, we discussed about the settlement. So to get an equation for settlement, in the questions, there are 2 things we need to find. So one is how much settlement happening, that is S, and how fast it is happening. So to find the S, we need an equation. So we are going to derive an equation here. So if you have a Q load applied and this portion where you have the reduce or the reducing the height, that is the settlement. And if you have H, thickness of the soil, you can say strain is change in the length divided by the length. So change in the length, change in the height is S, divided by the initial length or the initial height is H. So this you know this is the definition of strain. So if you apply that to the equation that we just derived, you can make the S subject and you can get an equation. So this equation is the equation for the settlement. So if you know how much the void ratio, change in the void ratio, initial void ratio, and the thickness of the soil layer, we can find out the settlement. So this is again another important equation that we will be using. Now let's see how we find out the settlement in the lab. We discussed about the odometer last week, but we used the odometer for questions, but we didn't know how it works. Now today we are going to learn how it works. So in the odometer, what is happening is so this is the apparatus. So you can see we have a water bath. So the apparatus is this whole thing we call the odometer, but we have this cylinder inside water, and in this cylinder you can see we keep the soil sample here, and we have 2 porous discs. So these 2 porous discs, porous stones, they provide the two-way drainage. So two-way drainage, and we have a ring here, so you can see the ring, and a loading cap where we apply the load. So in this, what we are doing is we change this. We change the load. We load and also we unload, and we find out the dial gauge reading. Dial gauge is measuring how this one is flowing. When we load, this soil settle. When the soil settle, dial gauge is moving. So we write down the dial gauge reading in different time intervals. So time, we measure the change in the dial gauge reading when we are changing the load with different times. So that's what we do in the odometer test. Is that clear?
Yeah, I think so.
Yeah, now when we go through this, it will be more clear. Let's see the procedure of the odometer test. An undisturbed soil sample is obtained from the base of the borehole and loaded under conditions of no lateral expansions, as the soil fits tightly in the odometer ring. So we don't let it to expand in the horizontal direction. So it should be tightly fit in the ring. Drainage is provided at the top and the bottom. So we discussed last week as well. Whenever we have odometer reading, it is two-way drainage of sample by aired porous discs. The succession of the load is applied to the sample. Under each increment of load, the load settlement response is measured. So we write down the dial gauge reading in regular times while we are changing the load until all settlements under the increment is complete. The magnitude of the loading is usually doubled. So when we changing the load, we double it all the time. If the first one is 20 kilopascals, the second loading will be 40, 80, 160. Likewise, we double the loading and we take the dial gauge reading in different time intervals. Generally, at some stage, an unloading reloading loop is conducted. So when we load, after that, so we are loading. This is the loading. When we load, what is happening is stress is increasing. Stress is the force divided by the area. So the pressure is increasing because we are loading, we are increasing the load. And while we are increasing the void ratio is decreasing. So it's expelled water. And after some time, we start to unload. When we unload, the stress decreases and the void ratio increases in a different rate. So you can see when we unload to the maximum, we unload everything, we are ended up here. So this is the loading curve and this is the unloading curve. So we need both of these. So we get the loading and the unloading curves while when we are doing this test. Okay, so we are done up to here. Any question, Sean?
No, not so far.
Okay, so at the end, what we are doing is, so here we don't know how to measure the void ratio yet. So you know how to measure the stress because you know the applied force. You know this force and you know the area. So you can find the stress here, effective stress. We do some examples, so we can calculate this. Now to find out the void ratio, the y-axis, let's see how we find the y-axis value to position these points here. At the end of the test, the sample is removed quickly from the apparatus and the final water content determined. So we find out the water content. We take the sample out and we find out the water content. For this, the final void ratio can be found. If you know the water content and if you know the GS, specific gravity of the soil, we can find out E. So this is the final E. So this is the E final. Because we do it at the end. From the height change in each increment, the final void ratio at the end of each increment can be formed by working backward. Now we work backward, and this equation is the one that you already use. It is not a new one. So that is this. We use this equation. So this is equals to strain is the change in the height divided by the original height is equals to delta E over 1 plus E naught. So I didn't put the minus sign here. So if you can, we in the odometer test, we are measuring the change in the height. This is the dial gauge reading and you know the initial height and you know the initial porosity of the soil. We can calculate it. So with this equation, you can find out, you can make the delta E the subject and you can find the delta E. When you find the delta E in different time intervals, you can add this delta E to this delta E and you can calculate backward. You can find out the E in different time intervals. Does that make sense or not? This is the final value. If you add, this is the lowest value, or we can't say lowest because loading and disloading will be different. So this is the final value. If you add the delta E to this, you get the previous value. When you add another delta E to this, you get the next previous one. So you are calculating backward. Your delta is not a constant because your dial gauge reading is not a constant all the time. It depending on the time, it is changing. Does that make sense?
Yeah. So looking at the graph, the finally is the lowest point, and then you're just working backwards.
Yes.
Yeah. Okay. Yep.
Okay. Now let's see. There are a few things that we need to understand. So there are two curves here. Virgin curve when loading. So that is when loading, you get a curve like this. So this one we call the virgin loading because the soil is not affected that is the virgin soil. It's not loaded before. It is the first time it is getting loaded. But unloading and reloading, but we can't find a soil like that. It's continuously getting affected by the stressors and reloading and loading. So when we do few times this test, you can see this one, this loop we call the unloading and reloading curve. And depending on the situation of our soil, if the soil is in the virgin condition, your delta E will be different. It is settlement is more. But if we have a soil which is in this condition, which has been loaded before, preloaded, the settlement is less because now it is going through this cycle. If that makes sense. Or not?
Yeah, that makes sense. So once you're unloading, it's already been
compressed.
Discussed. Yeah.
Yes.
Yeah. So you're working back. Yeah.
Yeah. Working back and forth, back and forth.
Yes. So essentially, you've got a soil sample in a container and you're slowly adding force on top of it. And when you reach the end, you're taking them back off again and reading the results. Yeah.
Yes. Yeah. So that's happening in the real case also, it's happening in the same way. So we build something, we demolish it and we build again, or else. So soil is undergoing stresses. So a long time ago, 100 years ago, we had something on that soil, but now we have another thing. So if we have a virgin soil, the settlement, it's going like this. However, in nature, in practice, we have this kind of soil in most of the cases. Even from the, I'll show you another. Yeah, later on I'll explain that. Okay, so so we have two curves here. Two virgin curve and the unloading and reloading curve. Pre-consolidation stress, let's see the stress history, the pre-consolidation stress. The maximum vertical effect stress the soil element has experienced in the past, that we call the pre-consolidation stress. That is the maximum vertical effective stress the soil element has experienced in the past. In the past, the maximum stress that has been experienced, that we call the pre-consolidation stress. So this is important because we are going to use this in our questions. For soil on virgin loading curve, that means this OPR curve, the pre-consolidation stress is the current effective stress. So you can say it is the first time the consolidation happening. So whatever you have at the moment, if you are here, your pre-consolidation stress is whatever you have here. So this one. So when you, it is the current value. If you are currently here, that will be this one. If you are currently here, that will be this one. If you are currently here, that will be this one. So likewise, along the OPR, your value will be the current value. Is that clear? Oh, no.
What would be the current value? You're saying that.
Just ignore this. So for example, so you are started here. Okay, so your current stress value. So this, what do we have here? This point has a, this is your void ratio at that point, and this is your this is a log scale, but you can calculate the stress. So you have the stress, you know the stress and the void ratio at this point, isn't it?
Yeah.
So currently the stress on the soil is this. So this is your current stress, isn't it? Yeah. So the maximum stress and the current stress is the same now, isn't it?
Yeah.
Yeah. Now, when you further loaded, you will reach this point. Now, previously you had this. Now you have come to this. So this is your current position, and this is your previous one. Now, what is the maximum? Current position or the previous stress? Current stress, isn't it? So your current stress will be your maximum stress all the time when you are in the OPR curve.
Right. Yeah.
Yes. So whenever you go here, that will be the current, the The maximum will be this. But when you consider the OP curve, or else QP curve, or else unloading, reloading, and unloading curve, the pre-consolidation stress is this one all the time, isn't it?
Right. Okay. So always from that point.
Yeah, it reached the maximum. So it's going back now. Whenever it's going back, the current value is less than less than this, isn't it?
Yeah.
So this will be your pre-consolidation stress.
Yeah, that makes sense now. Thank you.
Okay, so then because of this thing, we have two conditions here: normally consolidated soil, and we have over consolidated soil. So normal consolidated soil is the one which is along that virgin curve, where your current stress is equals to your maximum value. Then the soil is said to be normally consolidated. So when your current value is equals to your maximum, pre-consolidation stress, when your current value is equals to pre-consolidation stress, we call it the normally consolidated soil. If your current stress is less than your sigma p, then we call it over-consolidated soil. Over-consolidated means it has been stressed in past. It is pre-consolidated, like, you know, it's loaded before, not on the virgin coil, virgin curve. Does that make sense?
Yeah, that makes sense.
Okay, this is what I told you before as well. Soils are loaded in the past history, so such soils are less compressible and more stable, so they are safer. But the normally consolidated soils are loaded first time in the history to present applied effective stress. Such soils are more compressible, representing high settlement of the loading. So that we need to understand that. Okay, now let's see. For the same increase in the effective stress, change in void ratio for over the consolidation soil is less than the change in void ratio in the normally consolidated soil. So what's the meaning of that? How we can find the void ratio? Void ratio is the change here. So if you consider the normal consolidated soil, your void ratio is this long, the change in the void ratio. But if you consider the over-consolidated, your void ratio is this. So your void ratio in the over-consolidated is less than the normal consolidated. It's like when you just look at this, you can easily understand that, isn't it? Is that right?
Yeah, you can see it graphically quite easily.
Yeah, so this is always higher than this part. Therefore, settlement will generally be much smaller for structures built on over-consolidated soil. Again, we are telling the same thing. Most soils are over-consolidated to some degree. This can be due to the effect of shrinkage, swelling, soil on shrinkage, swelling on the soil, drying and wetting, as well as unloading due to erosion and overlying strata. So as I have mentioned in the practice, most of the soil that we find on the field is over-consolidated. So in this graph, there is an important parameter that is OCR. So distance from the virgin curve has an important influence on soil behavior. This is described by the OCR. OCR is over-consolidation ratio. And we are going to use this in the calculations. It's defined as the ratio of the pre-consolidation stress. So this is the pre-consolidation stress, which is the maximum value. Stress current divided by the current value. So when you consider the line here, it is always 1. Am I right? Isn't it? Because this line, the green line, your this is always equals to your current effective stress, isn't it? That's how we defined it, because it's not reached up to here when you consider a point in between, isn't it?
Yeah, so it's always one.
It's always
Calculate. Yeah.
but when you consider this part, it is what? Less than 1 or more than 1? Which one is higher? This is the highest value. So highest value divided by some smaller values, so it is always greater than 1. Is that right?
Yeah.
Yeah. Okay. Now, when you consider the curve that you get from the odometer test, we won't be able to get it nicely, because when we disturb the soil from the ground and when we put it in the ring in the odometer, it is disturbed. So we normally don't get this. We don't get this. We don't see that, but we can get the other curves. So with this curve, so we get something like this in the odometer test. So when we read with the time, the stress and the void ratio, so this is the void ratio and this is the log 10 to the power effective stress. When we plot that, we get the curve like this. Is that make sense or not? Because I told you in the odometer, we measuring the dial gauge reading. With the dial gauge reading, we can find out the E. And also we know how much we are loading. If we know how much we are loading, we can find this. So we can plot the log sigma dash and E. So when we plot it, we get something like this. Is that clear?
Yeah, okay. So when you're retrieving the sample, you're taking away some of the stress. Is that right?
It's already preloaded. It's like, yeah. So when we get this, it is very important to find this point from the results that you get from the odometer. So let's see how we find it, because it's not clear. We don't get it nice curve to find out. This is a curve. So this is not straight 2 lines like this. We don't get like this in the experiment. We get something going like this, and we can see a curved area here. So it is very important to look at this point and find out this value, because this value is important for all the calculations. Now let's see how we can find that value from a lab results. So you get a curve like this. So just for the time being, you do not this one. So you get this something like this. So you have a straight line, and then you have a small curve here, and you have another straight line. So you get something like this. So your NP, sigma P is not easy to find. So if you look at this, you don't see it as two intersection of 2 straight lines. Instead, you see a curve. So now let's see how we find out the P, that point, corresponding to this sigma dash P. So there is a procedure to follow. What you do is, first you find, you draw up, you locate the point A, which is the point of maximum curvature, and draw a tangent AB. So first you find the maximum curvature and you draw a tangent line at that point. Is that clear? So that is so AB. After that, what you do is you draw a horizontal line at A. So you are drawing this AC, which is horizontal. A is the maximum curvature, the point at the maximum curvature. Then what you do is you find this angle, you divide it into 2 equals. So bisect the angle. So I should have that. Yeah. So you draw AD, bisect 2 angle BAC. Then what we do is, then you extend this line. You extend this line, extend the RE. This is a straight line. You extend it, and the intersection of DA and this AR, this intersection point is your point P, which is corresponding to sigma P dash. So we found this. This is the way that we are finding it in the lab test. Is that clear?
Yep, that's clear.
Okay, now after that, so we have a nice curve now from the lab. Now we use this curve to find the parameters. So settlement, there are two settlement parameters, CR and CC. CR is recompression or rebound index, and the CC is compression index. Slope of the loading curve is, we call the CC. Slope of the unloading or reloading curve, we call that the CR. So you can find, when you have this graph, you can find the slope. Slope is the tan angle. So you can find it. However, in your questions, mostly this CR and CC will be given to you, because you are not going to do a lab test and you are not going to find this. However, if you do with the lab test, you can find this by plotting the graph. So these are the two settlement parameters, CR and CC, and they are important for us to do the calculations. Okay. Now there are three situations. The three situations are, this is very important because we are going to use these three situations in calculations. So three situations are these three. OC stress range, NC normal consolidation, that is this one. Over-consolidation, which is this one. If your points are, if your soil is in OC stress range, you can find out the CR and delta E using these two equations. If your soil is in the normal consolidation range, if it is firstly consolidating, you can find CC and delta E using this. If it is between it, if it is undergoing from OC to, sorry, from NC to OC, you have both. So you have both the conditions, and you have to consider both, and you add both together to find the final. Is that make sense or not? Don't worry about these log things for the time being. You actually don't need to know how. I can actually explain you if you want to. Let's explain. I think it's better. Okay, so what is CR? Can you, so let's, if I explain this, I think you can figure out the rest. So what do we mean by CR? CR is the
recompression. So once you unload it, it can.
It is the slope of this one, isn't it? Slope of this one. So how do we find the slope of that? You divide the y and the x. Am I right?
Yeah, right over right. Yeah.
So what is the y? Y is this minus this, isn't it?
Yes.
Or else the difference between these two. So
The
E1 minus E naught, yeah. Or E naught minus E1. That's like, you know, the change, the difference. And you divide by the x. What is x? X is this two, isn't it? And this is a log graph, isn't it? So x will be log 10 to the 10 this minus log this, isn't it?
Yep.
So we can write this as, what do we mean by this? Change in the void ratio. So I can write delta E. Do you agree?
Yes. And
then you can write this, this is a minus. So log minus, we can write as a division, isn't it?
Yep.
So you can write CR like this.
And then you put the minus at the front.
Yes, you can. You have to, because this is a minus. No? So this is a minus. Delta E is a minus. It is decreasing.
Yeah.
So To make this one the subject, so that is your this equation, you know how this came. And if you want to make the delta E the subject, you rearrange, and that will become minus CR times log this divided by this. So that is this equation. So that's how these equations came. You don't need to do it by yourself, but they are not like, we can find it, we can calculate them. Is it clear?
Yeah, that's clear.
Okay, so you can do the same to this and same to this, and the here you are coming from here to here, you are lying in both ways, so that you have to add both the delta E's to find this to the total. So total will be delta E1 plus delta E2. Okay, now we know we already discussed this. We can find the settlement using this equation. Can you remember in previous slides we discussed this?
Yep, that was taken from the week 1 stuff.
Week 1, and also here also we discussed, we can you remember here?
Yeah, changing the void becomes the thickness of the material.
Yeah.
Yeah, and then I think last week it was which way it was draining. That was another thing as well.
Yeah, that's right. So here now I told you in the settlement, we should know how much settlement happening and how fast it is happening. So we should be able to find this. So if you want to find this, I'm just using the equation. We found an equation for delta E. You substitute that one here. So you get an equation like this to find the settlement in OC, settlement in NC, settlement in extending from OC to normal. So when you have both together, you have this. So you can use this equation to find the settlement depending on what kind of what is the situation of the soil. If the soil is undergoing this, you just use this. If the soil is undergoing this, you are using this. If the soil is here, then you are using this. So we have 3 equations to work on. Is that clear?
Yeah, you just substituted in what we just did.
Yes, you just substitute the values. So in most of the cases, in your questions, this will be given to you. And this you know how to find it from week 1. Am I right?
Yep.
This one you found many weeks, how to find the effective stress, you know, if there are different ways. So you can use this, or else you can start with the basics and find it. The change in the stress, we did 1 week to find, we discussed this, how to find the change in the stress. Can you remember? So we can find that. Again, in the second equation, this will be given to you because otherwise you have to do the odometer test and find this angle, but this is given to you. And you know how to find this. This is the thickness of the soil layer that also will be given to you. So you can just substitute and find it. We are going to do a question, okay? So it's not hard when you do a question. So we need to know, we have 3 equations. First, we should select the right equation depending on our situation. After selecting the right equation, we just substitute the values and we are going to find the S. So it's not hard to find the S. Okay, so now let's before doing a question, let's see the steps that we need to follow when we are solving settlement questions. To calculate the settlement, it is necessary to find the initial, final, effective stress. So we need to know this initial and the final. And the pre-consolidation. So we first need to find these 3. We do a question, okay? So don't worry, we are trying to find this in the question. The initial stress can be calculated from the knowledge of overburden, the weight of the overlying soil. So this one we did, I think, in the week 3 or first few weeks, we knew how to find this. The initial and final pore pressure can be determined from the position of the water table. If you can remember, this one we found like this. Can you remember?
Yep.
Yeah. And initial and final pore pressure can be determined from the position of the water table. So you know this. You can use this and you can find out this. Am I right? That we know. In order to find the total stress necessary to find the increase in the total stress due to the applied load. So we are going to do that. Calculate the settlement of each sublayer and sum them together. So when we have many layers, we find the settlement in each layer separately and we add them together to find the total settlement. So that's how we do the questions. So soil profile divided into number of sublayers, as you see here. The second step is calculate initial effective stress using this equation. And calculate final stress. Final stress is always the initial stress times the stress increase. You know how to find the stress increase because we did in 1 week. Then calculate the settlement for each ith layer. So because when you have many layers, you need to take one at a time and you do separately. So you find the settlement for the first one. When you're finding that, you need to use the equation, one of these equations. These three equations are depending on where we are in the curve. Okay, so if you are here, you are using this one because your final is always less than your sigma p. So that is this. If you are here, your final is always equals to the MP, or else your final is more than the, so this is your P is more than the P, so you are using this equation. But if you are here, if you are in between, so if you are undergoing from here to here, then you have to use this equation. Does that make sense?
Yeah, I think so. Yep.
Okay. Then the fifth step is we sum up all the settlements and we find the total settlement. Settlement can be calculated in 2 ways. Last week we used this, if you can remember. Can you remember we used this? That is one method that we did in week 9. Now we are doing a different method, which is week 10. So I told you, you have one question in your final exam. So you may need both the knowledge to answer that question. Okay.
Right.
Okay, so that's all theory. Any question?
Not at the moment. I think do an example.
So this example is the same example that you have in week 9. I told you to try this. If you can remember, were you able to try this?
No, I didn't try it. Sorry.
Okay, so we are going to do the same question using today's method. Okay, so even though if you use last week method or this week method, you still should get the same value. So we are going to use today's method and we are going to solve this. Then we can try the other one, or else you can try the other one later on. Okay, now let's see how we do this. Okay, we have two kind of soil. We have gravel and we have clay. They have given us saturated, gamma saturated and gamma dry. And also they have given for the clay E, GS, CC and CR. All of these are given. Now let's read the question. Initially, the water table is 2 meters below the surface of the gravel. So initial stage. So this is the 0 when the time 0. So you need to find these ones using this initial situation. Then what is happening? If the water table rises to the surface of the gravel slowly over a period of time, and the surface loading induces an increase of total stress of 100 kilopascals at, so increase of total stress at A. So you know when we apply the force, it increases the stress. When it is increases, the increase is decreasing. So you have an increase here 100 kilopascals, but when you come to here, the increase is less, 60 kilopascals, because you can see it's a curve, is the tangent is decreasing. So, am I right? So your increase in stress is less when you go further down. So you have a 100 kilopascal of increase in stress at A and 60 kilopascals of increased stress. So this is the delta Z, and this is the delta Z at B. Am I right?
Yeah, that makes sense.
So the pre-consolidation, what is this? That isn't it. Soil is normally consolidated at B. Okay, so now these are the things that we know. We are going to use this and we are going to find out the settlement of the soil. Calculate the settlement. Okay, first we will take one by one layer by one layer. So if you consider, so this is what we have explained. Okay, now let's take the layer 1. So gravel, we have 4 layers actually. Gravel is, what can you say about the gravel? Are they consolidating from last week? Consolidation is happening when you have poorly drained soils, isn't it? So gravel is a drain. Gravel has initial settlement, elastic settlement, but it is ignorable, it is small. But it doesn't have consolidation happening in the gravel because gravel is fully drained, isn't it? It can be saturated, but it's not changing the volume. Like, if that makes sense. So in the gravel, we don't consider the settlement in the gravel. It's happening in the clay. So we have 2 clay layers, sublayer 1 and sublayer 2. When you consider the sublayer 1, the first clay layer, we need to find out this initial stress. We need this now. Am I right? Is that right?
Yeah, see initial stress, the saturated clay layers, what you're finding in sublayer 1?
Yes.
T equals to 0, or the depth of the layer.
Sorry, what's that?
Oh no, sorry, I'm ahead of myself. Initial state of A. You're just finding the saturated unit weight.
Yeah, I forgot to tell you.
Yeah.
I forgot to tell you one thing. So we know the curve is like this. The settlement curve is like this. Now we know this one is here. This is your P value. And initial value and final value. If your initial value and final value are staying here, if your initial and final are here, then you use NC curve. Sorry, not NC, OC curve, isn't it?
Yeah.
If you are here, you have to use the OC. So firstly, you need to find out where are you. So because you have 3 equations, we need to find out which one to use. So to find out which one to use, you need to know these 2, initial stress and the final stress. And you need to know relative positions. When you consider this one, if both of them are into the left-hand side, you have to use the equation for OC. Is that right?
Yeah.
So we need to find this. Okay. So if you are here, so this is, okay. So this is sigma P. In case if you are here, if your final and the initial are here, then which curve, which equations you use? NC equations, am I right? So again, to make sure that we are using NC equations, you need to know where is your N sigma 0 O and sigma F relative to sigma P. Sigma P is given 120. So you need to know what are these two values. If these two values are more than 120, you are going to select the NC equation, isn't it? Is that right?
Yeah.
Again, we need to find the sigma 0 and sigma final. And the last equation was what? Last equation was this, isn't it? So your sigma P is here, sigma P dash 120 is here. If your sigma 0 is here and sigma final is here, relatively, one is less, one is more, then which equation that you use? You use the third equation. Am I right?
Yeah.
So to first select which equation to use, you need to find sigma naught and sigma F. So that's what we are going to find first. Okay, so let's take the layer 1. And when you take the layer 1, to find the sigma naught, so initial condition. So this is the initial condition. Your water table is here. Layer 1 is the A. So when you consider the layers, clay layers, your settlement is not throughout the clay, it is not the same. So it is changing like this. Settlement is changing like this. But we consider the middle point because it is not a constant. So we consider always a middle point. So we are considering this middle point, which is 2 meters from here. Okay, now if you consider that point, how do we find the sigma initial? Sigma initial, sigma naught dash for A is equals to sigma final minus the pore water pressure. Do you agree with me?
Yes.
Okay, now we need to find the total stress, this one, and the pore water pressure. Let's find the total stress first. When you find the total stress, how do we find the total stress? Can you remember how to find the total stress? Total stress at here. How do we find it? So what do we have? We have gravel. This gravel layer is dry gravel layer. Am I right? So thickness is 2. So am I right?
Yep. You
Yes.
have that. The next layer.
Next layer is what? It is 3 meters and it is saturated. Am I right? Because we have our water table over there.
Yep.
And the third layer is what?
It's our clay.
Clay layer.
Take it from the
It
middle
is
point.
2 meters only, isn't it?
Yep.
And we need to know the saturated. So 2 times gamma sat. So sorry, gamma sat. So how do we find the gamma sat? Can you remember? We used this equation in the first week. So gamma sat can be found using this equation. GS is given to us, E is given to us. We know this one. So we put the numbers in this. So we put everything and we can find the gamma sat for this. And it is 19.6. Is that clear?
Yep.
Okay, now we found the total stress. So how do we find the pore water pressure?
That'd be 9.81 times 5. Oh, it's written right there. The depth. Yep.
So 3 plus 2 is 5. So 9.81 times 5. So we minus this 2 and we find the initial value for this. Okay, so if you understood this, can you find me the final value? So this is less than 120. So we are still in the left-hand side, over-consolidation side. Now we need to check the final as well. Can I give you a few minutes for you to do the final? What is happening when it is final? Only difference is what?
Is that, sorry, the question is at the water table?
Water table increases and also you have a additional stress at A, isn't it?
Additional stress at A.
You have a stress increase, 100 kilopascal stress increase.
Oh, so you have to add an additional 100 onto that
Yes,
loading.
in the total, yeah. So you have 100. So I'll give you a few minutes for you to try that. Water table is high and you have additional stress. The rest is the same.
I've got 248.12 for the
Which
yeah, for
one?
total stress.
Yes, that's right. 1248.12. That's right, yes. For water pressure now, you have a longer, high value for H.
It'd just be that extra layer with an extra
Extra,
7 times.
yeah.
Yeah, it's
7 times, yeah. So you minus this 2 and you get that value for the effective stress. So now what you can say, layer 1, initial, final, and the sigma P, when you compare these, where are we? So this is 120. Initial value was what? 91 point something, 91.07. Now where are we? 179.45. Which equation we need to use?
The third equation, because we're over.
Yes, that's
Yeah.
right. So we use the third one. So we use the third. Let's see how we can use it. So
So we have all the information we need just to put into that, do we? Yeah. So we don't actually have to calculate anything else.
yes, so you have everything. Just put the values in this third equation. CR is known. E is known. E given. Initial value given. The H is given. These ones you found. Sigma P given. This is 120.
Sigma P is the 120 that was.
Yes, this you found 90 something. And this one is 120 again. And this you found 179.
So the H initial is at the height of the layer?
Height of the layer 4 meters.
Right. I'm just writing it down.
Yeah.
The CR was 0.05. Yeah. It's right down. And C, we don't need, we do need C.
0.05 and 0.2.
0.02?
0.2, yeah.
0.2, yeah.
0.8.
It's a fairly long equation.
Yes. And you can do the same thing in the same, like the method you can use the method that we used last week to do the same thing.
Will it be like a question telling us which one to use, or will it just be a question?
I can't remember. I'll have a look at the end.
It's going to take me a while to put it in my calculator. I'll have a crack.
Yeah.
I get 0.097.
Yeah,
Or
yeah.
1, yeah.
0.09, yes, meters. So that's the settlement in the layer 1. So that is just S1. Okay, we only done half of the question. Half, not half, 1/4 of the question. No, well, half of the question. Yes.
Because now we have to find out layer B as well.
Yes. So can you find the layer B? First, can you find which equation to use?
Yep, I can do that now. Yep.
So just find the signal, initial and final.
For the initial, I got 216.36. I'll do the pore water pressure next.
Yeah, that's right. You minus the pore water pressure. It's easy, isn't it? 3,
Yeah.
4, 6,
So
7, 8, 9. 9 times, isn't it?
isn't it 11? Because we're going from the center of B.
3. Initially, you have the water table at the second gravel layer.
Oh, yeah, true. I've gone from the top. So it would be, yes, it would be 9.
Yeah. Nine times 9.81.
It's 88.29.
So 128, isn't it?
Minus 260. 128.2. Yep.
Yeah. So it is in the so let's find the final as well. When you do final, you have to add 60 to the total, and your water table is up now.
Where did the 60 come from in the question? Sorry, it said it
Yes,
was
yeah. Stress
100.
increase. Can you remember there is a stress increase? Here it
At
was
the end.
100 and here it was 60.
Yes, I remember it saying it somewhere, and then it gave P at 120. Okay. They're at 284. And that for water pressure would be 107, which I got last time.
That's right. Yes. Yeah. So, yeah.
And you get 176.45.
Yeah, that's right. So which equation we should use? OC, NC, or the third one?
The second one, we should
NC, isn't it?
NC, yes.
Okay.
Normal compaction. We should have passed 120 on both of them.
Yes, in the right hand side. So where is the equation? Yeah, this one. The second one. It's a short one.
And I got 0.6. That's too much. That's wrong. Let me redo it. Hang on.
0.06, yes, that's right.
No, sorry, I got 0.6. It's way too big compared to the other one.
Oh, okay.
I've just put in the calculator wrong. So 0.2. Yeah, that's what I did. I'll just redo it.
Okay.
Yeah, it just looks like a me problem. I keep putting it in wrong.
You still don't get it? Maybe
Yeah.
the brackets. So do you put the brackets here? This part is the log part 4 is not inside.
Ah, yeah, okay. I'm doing that part. Yeah.
Okay. Now that is the settlement of the second sublayer. To find the total, we need to add these two together and we get the total settlement. So that's it. This is a full question, but I think in the tutorial you have much smaller questions. So if you do this, you should be able to do all the questions in the tutorial. It's not hard.
It's just very long.
Sorry, what's that?
It's just very sort of long.
Yeah. Yeah, but it's not hard. Just the equations are a bit long, but it's very simple. You just find the initial, final, and then you just find out which equation to use. Just put the values in the equation. That's it.
Yep.
Yeah. So that's for this one. I missed one question from the last week tutorial, which I will do in the next tutorial.
Is next week our last?
No.
Next lesson, sorry, next Wednesday.
Yeah, next Wednesday is our last class, yes.
Okay. Are you going to do any revision or anything like that overall, or is it just going to be the last?
We'll do the last tutorial, and if you have any difficult sections, we can go through. Otherwise, I think that if you do all the tutorials, your questions in the exam paper is very similar to the questions in the tutorial. So if you are confident of doing all the tutorial questions by yourself, I don't think you find any difficulty in answering the questions and also it's